that. Okay, what we do need to dwell on is what's coming up for this, our awesome astronomy class. So today will be the final homework. Huzzah! Yay!
Is it like work all of the homework combined? You just file in your office and get an A on it and you pass the class?
No, but it is a homework assignment. Okay, on Friday, I will review in class on Friday, and we'll have, that says paper lab final. Obviously, we had the weather interfered last night with our plans of getting everybody through. So we got 4 people through, which leaves 8 people that haven't done it. In an unusual thing, I usually say, probation closes at 5 p.m. on Friday. Anything that's going to get credit has to be done by 5 p.m. on Friday. But because of the problem with not being able to finish last night because of the weather, I'm going to have, let's consider this here a provisional and if sometime before Wednesday night, that is inclusive of Wednesday night, but that's my, and even though Yari already has it done, but I have to turn in grades for Yari on Thursday. So anytime between now and next Wednesday evening, if it's clear, give me a call. There are a few exceptions, like Friday night. I will not do it on Friday night. And tomorrow night during the Raider game, I also will not do it.
What if they bring the game out with us and we can watch it together while we do it?
You can stream it.
No,
Who they play?
the cheats, yeah.
Well, they got to change.
Well, we're 10-2. Of course, we got cheats.
So if
But
you can't.
It's not like they're playing the favorites. And then I'm like they're playing the favorites.
I'm going to have people over to watch it.
So if we can't get it done by Wednesday of next week, then when can we take it on paper?
We're going to do it on paper Friday. That is 2 days from now.
And so then if.
So I will keep those. If you don't go outside to do it, then I'll count that as your score on it.
Okay.
So that's why I said we'll count as a provisional. If you get a better score from doing it outside, which it would always be better doing it outside, then that will take precedence. But we have this in case. And then next Monday at 1 p.m. is the final exam. So we're almost done. Now I know it's waste class time to do it, but I have to apologize. We're not going to get to talking about the Big Bang Theory. And especially, in a school where, we believe in creation, generally speaking, it's a really important thing to talk some about that, and I didn't get to it. I apologize, because if you understand more about the Big Bang Theory, you're better prepared to say whether you accept it or not.
Hey, if the TV is telling me anything.
Okay, so we got their answer. TV hasn't taught you anything. What were you going to say?
The whole universe was made in a hot, dead space. You were in 14 million years ago. Expected suddenly.
Yes, I do know a little of the lyrics to Big Bang Theory's theme song. Okay, so today we're going to, yes, question. It is cumulative, yes.
Is it new questions or do you reuse questions from your old tests?
There may be some reused. They're taken from the same database. We have used the majority of the questions in the database. There aren't that many in it. So there probably will be a fair amount that are reused, but there will also be questions that are brand new to you.
From these sections that we've covered that haven't been on the test so far. So we've been covering sections after this past test that haven't been tested over so far. Those will be included on the final.
Yes.
Questions.
Yeah.
Okay.
But I think you have practice questions that have them.
Okay.
Daniel.
So you do have those practice questions on Moodle,
Yeah.
like you did the other exam.
Yeah. Okay, so today is going to be our only day talking about galaxies. So I have here a pretty picture of a galaxy like the Milky Way galaxy. Make sure we all clearly understand that this is not a photograph of the Milky Way galaxy. You can't get outside of the galaxy to take a picture of the galaxy. We can take pictures of other galaxies like the Andromeda galaxy and use that to help shape what we think our galaxy looks like. This reminds me, I got carried away looking up when the test was and forgot to start.
Recording?
No, I'm recording. We have this all on tape. What I don't have is the ability to take in your answers on the clickers right now, but I'll just set that up as time goes on. Maybe. I've told to start. So this here was the last slide we had last class period. That was just going over when you look at a cluster, like a globular cluster or open cluster, you see stars that you can then put on an HR diagram, and you're seeing stars of all different masses at the same age. And so that's a big help in helping you put together how stars age. You can take globular clusters that are different ages and just stack them kind of like a flip book, and just flip through it and see how the stars progress in time by looking from one globular cluster to the next. So this is a couple pictures of different globular clusters at different ages to give us that information. So the first picture is showing a very young cluster. That young cluster has stars on the main sequence down to the point where they're still forming. Question, Gabby?
Sorry, I have one more question about the final before.
Yes.
Is there any short answer? Are there any short answer questions on it, or is it just multiple choice?
There is the same question as on the first exam, but with a different example. That is with the scientific method.
Okay.
I think that's the only one. That's my think. Okay, the second picture shows a cluster that's a little bit older. It's a little bit older, so those low mass stars have joined the main sequence. Then we get a little older, and we have some stars that have left the main sequence and some that are in the process of leaving. Keep going, and you have more stars leaving the main sequence. And so you can just map a certain mass and see how it moved throughout time, and then that's how we understand the time sequence for stars. So we can't observe a star going from birth to death. Not possible. Why is it not possible for us to observe? I know it's ridiculous to even ask the question, but why is it not possible for us to observe a star going from birth to death?
We die before it happens.
Yeah, the time is way too long. But using the HR diagram, we can get that information by looking at different clusters and mapping them. So we really do have actual measurements to tell us about the life sequence of stars of different masses by comparing the information from different clusters. So, when I look at that, oftentimes you'll have people who kind of mock the science of astronomy, saying this is what the universe, was like this, stars take this long and so on. But there's actually measurements that we can make to give us that picture. It's not even just a computer model in this case. It's actual measurements to give us, this is what the life sequence looks like. Trying to move that. There we go. Now move it again. Now, when we look at stars, we tend to see the brightest stars out there. Pretty obvious. The ones that we can see are the ones we see. The ones that are faint, we can't see, and hence we don't see them. Right? It doesn't take a genius to figure that one out. So when we look out at the stars, we see a lot of O's and B's. What can you tell me about an O or a B star? They're what? Luminous. Okay, they're very luminous because they are very hot. And these very hot stars also tend to be pretty big because you have to have a large mass to be very hot. So they're big stars that are very hot. They put off a huge amount of light. And so it makes sense that most of what we see are O's and B's. But if we look at a cluster, that cluster should be a representative setting of all of the different types of stars. And we can start counting in the cluster, how many stars do we have of this mass, how many stars do we have of this mass and of this mass. And what do you think is the most common mass of a star? Really big, really small, or middle? Okay, we have somebody who said in the middle. Now, I use this as, I think, my final exam question, the observation. If you actually map them, so you have mass, and so down here you have 0.08 solar masses, and out here 150 solar masses. And here's the percentage of stars. It actually looks like this. The vast, vast majority of stars are down here in the low mass region. So when you have a cloud, molecular cloud that has a shock wave go through it and things break off, you have the vast majority of the stars that are forming are small little things, but you get a few bigger ones. And those few bigger ones are the ones we tend to see a lot of. Now, where is our sun on this diagram? We have a mass of 1. And so we're somewhere down on this side. Yes, it's not a linear scale. You do it as a logarithmic scale. Otherwise, it would go like if you did on a... but the sun is somewhere here. It's on the low side of stars, right? Much less than 150, but much more than 0.08. And so are there a lot of sun-like stars? Yeah, there are. But there are a lot more that are smaller than the sun. A lot less that are larger than the sun compared to the smaller. Okay. Our first of the clicker questions, everything's our first. It's also our only, so make sure you answer. Unfortunately, I didn't start the presentation. I just had it up and right. So you can answer starting now. What is the name of the galaxy within which we, you and me, reside? I know it's a tough one.
What are those things on the side?
Those were answers given by another class that I did not notice was there.
That's why I went,
I totally didn't see them. Well, Jessica, do you have a clicker?
Yeah.
Okay. So you agreed with these people. You guys put all 12. Said it's the Milky Way galaxy. Good call. That was all you. I haven't talked about the Milky Way galaxy. You guys knew that. Nobody was confused by the Snickers galaxy. Of course, I didn't put the S on that.
You should change that to Oprah. Just hear people do it.
True story, at least as I understand it. Oprah was supposed to be named after the biblical character, Ruth and Naomi and Orpha, but letters got transposed. Okay, the Andromeda Galaxy. Clearly, we're not the Andromeda Galaxy. That's the one you have to point out during the lab final.
Yes. I can't believe it.
And we are part of the local group of galaxies. We're not the local galaxy. We're the local part of the local group of galaxies. Okay, that out of the way. Here is what the Milky Way galaxy looks like if you if you take a picture showing the entire sky. You might notice that the person who took this was no idiot. They took the picture when the Milky Way galaxy was going directly overhead so that it forms what looks like a straight line. If they'd taken it some other time, it would have looked like it had some curve to it. This line that you see was long observed by humans, and so the Romans called it the Via Galactica, I think it was, Via Lactea, which means the Milky Road, and the Greeks called it Galaxies Kyklos or something to that effect. I've got the words on the rest of the slide to show it, which once again is saying it's a milky thing. And so taking those, we have given the name to our galaxy of Milky Way, which would be the Latin word, the Latin name for it. And we call the entire group of things galaxies for the Greek word. So people long observed these. Now, you've gone out, I think we saw it when we were out at Gary Walter's house, right? The Milky Way. And it just pretty much looks like a cloud in the sky when you look at it. But that cloud is actually the combined light of millions upon millions of stars giving us what looks like a cloud. So when you look here, the Milky Way galaxy, what you see is this feature that is inside of those bars.
Is that the Orion Home?
Excuse me?
Is that the Orion Home? The Orion Home, I guess.
Oh, I don't know what way this is looking. I didn't pay attention. I can't see enough detail in, bright stars versus dim stars to see any constellations. So I don't know. So when we look at this, we can see there's something there. Here's the actual names: Galaxies, Kyklos, or Kuklos. I've seen it written both with a U or a Y there. My Greek scholars might be able to tell me, Yeah, do you know this word? Doesn't appear in the Bible. So when we look at it, we see that, and what we want to understand is what's going on. Now, the first thing is, it appears to be a stripe across the sky, but that stripe, as the Earth rotates, we see that stripe going all the way around. And so we can take this and say, it must be that we have stars all the way around us like this. So it's like a wheel around us. And so people have tried to put into models what they think this is. And one of the early models that came before this picture was a model that said that the galaxy was essentially a grindstone. That is, you have a stone that's yay thick and this big around. And that we had a bunch of stars and stuff in that stone, if you will, and we're within it. And so William Herschel, the same person who found Georgia Sideris, Georgia Star, what we now know as Uranus. He set out to try to map, I think with his sister, to try to map the Milky Way galaxy. And so he said, if I see more stars in one direction, that means the galaxy must go farther out, because he figured that the stars are spread about evenly throughout, and if you see more, that means that it's just farther out before you get to the end. And so he measured periodically all the way around the circle of the Milky Way galaxy. And he said, okay, I got 567 in this angle here, 563 here, 490, and so on. And then he just mapped it out to come up with that picture there. That picture that says we're shaped more like an arrowhead. So it was an improvement. It turns out it's not perfect. In fact, it's not correct, but it's an improvement. And Captain Jacobus, I don't know how to pronounce that. Probably Jacobus, right? Captain set out to improve on this, so he used better equipment with the same idea. And with his better equipment, he came up with saying that the universe was essentially an ellipsoid. That is like a rotated ellipse, so it's spread out, three-dimensional. That's 18 kiloparsecs on one side, 3 kiloparsecs on the other, and the sun is a little bit offset from the center. That's actually a lot better. Yes, still wrong, but a lot better. The real understanding of the galaxy and where we are came from Harlow Shapley. So Shapley, in studying the universe, as we know it, he noticed that there were a bunch of globular clusters that were pretty much centered somewhere in the direction of Sagittarius. And he said, okay, now if our galaxy has a center, the globular clusters should be clustered around the center. And since these globular clusters are all over on one side, then the center of the Milky Way galaxy must be over towards Sagittarius from where we sit. Now, that was the start of this, but his real breakthrough was with the discovery of the Cepheid variables, that there is a relationship between the luminosity and the period. And using that luminosity-period relationship, he was able to identify Cepheid variables in these different globular clusters, and using the brightness of that variable and the luminosity it has to have based on its period, calculate the distance. And so he calculated the distance to these clusters and saw that, yeah, they formed a basically symmetrical cluster centered over here. He said the center of that cluster must be where the center of the Milky Way galaxy is. There's actually famous debates he had about, the center is us, no, the center is over there. He argued it's over there. It turns out that his calculation of where the center of the Milky Way galaxy is off. That's often the case. You don't take into account things like the interstellar reddening as light goes through what we call the interstellar medium, mostly vacuum. There's a little gas, and that little gas causes blue light to be scattered away, and you have more red light. And it also, of course, is going to make it so you actually have a dimmer light than you expect because of the light that you're missing, that blue light. And so that caused him to be off in his distance calculations. What were you saying?
I thought you were saying center of the universe instead of center of the galaxy, because the center of the universe is pretty much everywhere.
Right. At that time, they would have thought them the same. Now we know that, well, actually, maybe not at that time.
No, they're probably not at the time.
Historically, like we go back to the time of Copernicus, they thought that was the same question.
Yeah, you know what I'm saying.
Yeah. So it's to Shapley's credit that we now know the center of the Milky Way galaxy is out there toward Sagittarius. Now, later on, we'll get to more direct evidence of where the center is and how we can say, well, Shapley was wrong. But it's a step forward in understanding. So based on all of the understanding we have, this is, of course, the same as the picture from the opening slide. What we believe the dimensions and shape of the Milky Way galaxy are. So it's about 30 kiloparsecs. Notice the contrast, sharp contrast there. About 30 kiloparsecs, or 100,000 light years from one side of the Milky Way galaxy to the other. Okay, pretty big distance. And the sun is about 8 kiloparsecs away from the center. So the sun, the radius is 15 kiloparsecs, that's half of 30. And the sun is about 8 kiloparsecs away, so we're a little bit more than half of the radius outward from the center of the Milky Way galaxy. But more important than that is the actual shape. The left view there is a top view. That's looking down, you see the entire shape of it looks like a pinwheel. And then we have a side view. And notice in the side view, you see that there are stars that are both above and below that disk. That region there we call the halo. So the region above and below, it's called the halo. And so we have stars out there in the halo. And actually, this stuff here would probably also be halo. That's the disk. And then we have in here a nuclear bulge with the galactic bulge, which has the nucleus of the galaxy in there. And so the important things to know are regions in our galaxy are the three pieces. There's the halo, there's the disk, and there's that bulge in the center. So studying these stars, astronomers found distinct differences between the stars in the disk and the stars in the halo. The stars in the disk tend to be younger, and you have lots of stars that are bright, hot, blue stars. Now, of course, remember, percentage-wise, that's a small percentage of the total stars there. But compared to the halo, you have a lot of them in the disk. The halo on the other side, as well as the central bulge, has stars that are older stars. It doesn't have the hot, bright stars. Why do we have that older, younger separation? If you have a type O star, you know it's relatively young because type O stars don't live long lives. So if a type O star exists, compared to other stars, it's a young star. And so we can take that to say that the disk has young stars. But the halo and the bulge don't have blue stars, hence they don't have young stars, is our conclusion. They're just old stars. And so names were given to these. The disk stars are called population 1. And the halo I'm just going to go with halo. The halo stars are called population 2. And I like to think of these to make sure I keep them in line like I would with, two kids. I have a kid that's a 1-year-old and a kid that's a 2-year-old. Which one's older? The 2-year-old. And it's the same thing here. The population 2 stars are the older stars. The population 1 stars are the young ones. And our understanding of these gets more interesting. Here is some details about the two different types of stars. The population 1 stars are, of course, the disk ones, concentrated in the arm. And you have young stars, young like a few billion years old. You and me would consider that very old, right? But compared to stars, that's young. You have an overall blue look to it because the hot stars put off so much more light that they give you the overall color, if they exist there. So you have that blue color. They have pretty much circular orbits in the disk. And really, really important is the bottom line. Their composition. They're found to be about 3% elements that are what we call in astronomy metals. Everywhere else in life we would not call them metals. But in astronomy, if it's not hydrogen and it's not helium, it's a metal. So that 3% composition is elements that are bigger than helium. Where are elements bigger than helium formed? How are they formed? They are formed in the death of high-mass stars. So these population 1 stars, the disk and it says concentrated in the arms, those stars have stardust from other stars that have died before them. If you look at the halo and bulge stars, they're older, they're reddish, they're going in random orbits. They may be highly eccentric orbits, not close to circular, going at random angles around the bulge. And they have low amounts of heavy elements, low amounts of elements bigger than helium. So if they have low amounts of elements bigger than helium, then they must have been made by more pristine material that had not had a star in the vicinity die. So what makes the difference in a population 1 and a population 2 star? Yari's been mouthing things, but not saying a lot enough for me to hear. The primary difference is the population 1 stars are 2nd generation, or maybe 3rd generation stars. Other stars have been born, lived, and died before they were formed, and so they have parts of dead stars in them. Whereas the population 2 stars are more pristine, didn't have as much death before them, so they don't have as much. In fact, there's a 3rd population called the population 3. I'll come back to that. The population 3 are perfectly pristine, just hydrogen and helium. Because hydrogen and helium, we're not going to get to the Big Bang, but hydrogen and helium are elements that could have been created from the Big Bang on without stars. But anything bigger than helium had to have been formed from the death of the star. So population 3 would be the very first stars. Now, if the very first stars were big, they will have already died. If they were small, as in your homework problem, Yari, I know, worked it out. If you have a small star, it won't be old enough to have died yet. So you'll still have in existence population 3 stars if they're small mass. Population 2 formed after only a few stars had died in the vicinity. Population 3, lots of stars have died in the vicinity. So that's the difference in these populations. When we look at the Milky Way galaxy, we find the population 1 stars in the disk. So what does that tell you is going on in the disk of the galaxy? You have O's and B's, and you have population 1. What do those two things tell you? Okay, O's and B's are hot. They're large. Their lifetimes are short. So you have short lifetime stars that still exist, which means that you must be still relatively close to stars being made in the disk. So basically what that tells us is stars are still being made in the disk. In the halo, you don't have any of these young stars. You only have old stars. Conclusion, stars aren't being made in the halo. What we have in the halo are remnants from the early days of the galaxy. But what we have in the disk are still being made. Why? Well, the theory is actually shown on this slide here. The theory is that we started with a roughly spherical cloud of gas, but because of rotation, the gas started flattening out. Now, if you had stars that formed early, they could be formed anywhere in that sphere. And so you have some stars that were formed out here, some that were formed here, and so on, going in crazy orbits. But over time, as it flattened out, collisions made everything go pretty much in uniform circles, and that's where we're having our stars form now, where we have all the gas going in uniform circles. So we have an understanding of, based on the types of stars and the types of orbits of the stars in the disk versus the halo, the gas cloud flattening out to make the disk. Now, if we look at the disk, here's a picture showing bright stars observed from Earth. And basically, we only see stars in our arm of the galaxy and one arm on either side. There's too much stuff out there for us to see beyond that. That's where the method of Herschel was flawed. Herschel just said, the more stars I see, the farther out it goes. Well, you can only see so many stars before you just can't detect them anymore because there's so much stuff between you and any other stars. You know, if I have a light here and a much fainter light in the distance, I'm not going to see that fainter light in the distance. And so we basically can't see many stars other than these arms. The arms are bands where we see lots of stars. And so the band that we're in is called the Orion Cygnus, because on one side, we look in the arm we're in one direction, we see the constellation Orion. If we look in the arm we're in the opposite direction, we see Cygnus. So that's why it's the Orion Cygnus arm. The arm closer to the center of the Milky Way galaxy is the Sagittarius arm, because we see Sagittarius in the direction toward the center of the Milky Way galaxy. The one pointing away from the center of the Milky Way galaxy is the Perseus arm. So we see stars, and you can see the stars. This is only mapping O's and B's. We map O's and B's. We call them spiral arm tracers. I guess I don't have them here, so. Dude, sometimes my handwriting slays me. O and B stars are called spiral arm tracers because, number one, they're the easy ones to find. Number two, they have short lifetimes. So if you find an O or a B, you know, well, the spiral arm must be somewhere in this vicinity. And so tracing those out, those blue lines are the spiral arms that they trace out based on where they find these spiral arm tracers. Is the sun an O or a B star? No. Since the sun is not an O or a B star, it's not part of the recent star formation in our arm. It's just random luck that we happen to be in one of these arms right now. We could be anywhere out here because we formed a long time ago, our sun and our solar system. So it's just random luck that we're in, or maybe random bad luck if you prefer, that we're in one of these spiral arms. We could just as easily have been out here in between, because the spiral arms are simply where stars are forming right now. And we happen to be in a region where stars are forming right now. This here is one of the coolest pictures I think I can show you. This is a very recent means within the last 2 years, picture showing stars from our galaxy in blue and stars from the Sagittarius dwarf galaxy in red. What's the Sagittarius dwarf galaxy? It's a galaxy that is currently being assimilated by the Milky Way galaxy. When galaxies collide, I saw the coolest GIF on Facebook this morning. It was a computer animation of what happens when a star gets too close to a black hole. And you have just a little star, gets close to the black hole. Of course, what's going to happen to the speed of the star when it gets close to the black hole? It increases. So all of a sudden it starts zipping toward the black hole. As you get close to the black hole, the tidal forces get bigger, right? That means that the stuff that's just a little bit closer is pulled a lot stronger than the stuff that's a little bit farther away. And so the star gets completely shredded, and you just have gas spread out everywhere. And then that gas is doing stuff like this as it goes out and is pulled back by the gravity of the black hole.
What are the stars bigger? Because it's more massive than the black hole.
Well, that is certainly possible, since the largest known black hole is smaller than the largest known star in mass. But
Because the star is more black hole.
you're not going to be able to deform the black hole. I don't know. I mean, I have to think about it more carefully. But it's a good question. So what's going on here is essentially the same thing, but this is now with galaxies. The Sagittarius dwarf galaxy got close enough to the Milky Way galaxy that it was pulled in by the Milky Way galaxy's gravity, and its core is down there, somewhere close to the middle of the galaxy, and it's being pulled around, kind of like you're playing crack the whip. Somebody stops and pulls, and everybody goes, the farther away you are, the faster you go, you're being pulled around. And so the ones out the end are being flung crazy out there. And one of the things that's most awesome about this picture is where the sun is. I'm turning off the lights, to hopefully you can see a little better. The sun is here, and notice the tail of the Sagittarius dwarf galaxy is here where the sun is. So we're in the vicinity where stars from that galaxy are passing through the disk of our galaxy. How in the world can they tell which galaxy a star belongs to?
Composition or type of star.
Okay, composition or type of star is a start.
Computer model.
Actually, not this time. What direction will a star in our galaxy be orbiting?
It'll be orbiting around.
It'll be going around a circle. If it's one of the stars that's been flung abroad by this, what direction will it be orbiting? It'll be going straight through the disk at this point. And so by the direction we're traveling, we know that we're not one of the stars from that Sagittarius dwarf galaxy. We belong here, probably. There is also the chance that we might have come from somewhere else and be coming through the galaxy and, be assimilated from a different direction. But we can be sure that we're not part of that. You have a question?
When galaxies collide, they get their combine and throw each other off, right?
They do both. It's not one or the other. It does both. So some stars get thrown off all on their own at very high speeds. Other ones are stuck in the new galaxy. So we call this process galactic cannibalism.
Somebody tell them that cannibalism is illegal?
No, we won't. Let's look at some other types of galaxies. We'll get back to talking more about the Milky Way galaxy. No, we won't. No, we won't, because I have to do teacher evaluation. You should have gotten an email about the start of class, or you can just go to Moodle, and there is a link at the beginning of Moodle. Let me go to Moodle. That should show up there that says teacher evaluation. It became available, the link, 10 minutes ago from me. And you can do it on your smartphone. You can do it on your computer. You truthfully could go home and do it, but we want you to do it. And so we're giving you time here in class